Assalamu alaikum dear students. I welcome you to the 7th lecture of probability and stochastic processes. This is 7th lecture, which means start of the 3rd week. So I hope that during the first 2 weeks, the 6 lectures, you had found interesting applications of probability theory and have continued your search for better understanding of the ideas discussed. Your search should include good textbooks, the class handouts, the web resources, and any other piece of information that you can get your hands on to have a better understanding of probability theory. So far, we have concentrated on finite sample spaces, those random experiments where total outcomes are finite. Today, we'll extend our horizon and start discussions on those random experiments where the set of total possible outcomes is infinite, possibly uncountably infinite. Before we do that, we should continue with our discussion from the previous lecture where we wanted to discuss one application of Bayes' rule but could not because of shortage of time. That application was the observation that if you are told that a certain person unknown to you, randomly selected, and then you are informed about that randomly selected person that person owns a house in DHA, posh community of Lahore, then what can you say about professional affiliation of that person? And the common perception is that if a person owns a big house in DHA Lahore, most probably he is an army officer. What is the reason behind this perception? And we are going to analyze this through the application of Bayes' rule. Before you apply the Bayes' rule on this problem, you should have a clear understanding that what is sample space and what is the random experiment that we are considering. The sample space is all residents of Lahore, and the event that we are considering is that a randomly selected resident of Lahore owns a big house in DHA Lahore. For this discussion, we are going to partition the population of Lahore into two sets. Set B1 represents the civilians living in Lahore, and set B2 represents the officers of Pakistan Army who live in Lahore. For the sake of argument, you can assume that 99% of Lahore's population consists of civilians and only 1% of Lahore's population is army officers. So that is the probability of partition B1, 99%, and partition B2, 1%. But if we go further, what is the probability of a civilian owning a big house in DHA? We can assume it to be 0.1%, that 1 out of every 1,000 civilians owns a house in DHA. But the way new sectors of DHA are assigned to different people, we know that a majority of army officers own a house in DHA. So out of that 1% population of army officers, suppose 85% of them own a house in DHA. If you put all these things together to form the Bayes' rule, you will see, as shown in this slide, that the whole population of Lahore is divided into two partitions, B1 and B2. B1 consists of civilians and it contains 99% of Lahore's population, and in this figure it is a big partition on the left. The very thin partition on the right represents 1% army officers, and the green portion in each partition represents those people, civilians on the left and army officers on the right, who do own a big house in DHA. As you can see, only 1% of civilians and approximately 85% of army officers own a house in DHA. Now, the Bayes rule says that the conditioning event is this knowledge that a randomly selected person owns a house. And this conditioning event is represented by the total green area in this figure. So what is the probability that a randomly selected resident of Lahore owns a house and is an army officer is represented by the ratio of the green vertically thin stripe divided by the total green area, which is substantial. And similarly, the probability of a randomly selected resident of Lahore who owns a house in DHA Lahore and is a civilian is quite small. So Bayes rule gives you an opportunity to find out information about random phenomena indirectly through observations of end results. Well, this brings us to the end of our discussion on Bayes rule. So far, we have studied applications of set theoretic analysis to analysis of random phenomena. In particular, we have discussed joint probabilities, conditional probabilities, a priori probabilities, a posteriori probabilities, and combine them all to get Bayes rule. So far, we have limited ourselves to discussion of those random events where the set of total possible outcomes, the sample space, is finite. Today, we are going to extend this with discussion on those events where the set of all possible outcomes is not finite. It is infinite and possibly uncountably infinite. Let's start with the old example of coin toss. In usual practice, we take a coin which has two distinct sides. We call them head and tail. And if we take this coin and throw it up in the air and let it fall and come to a stop at ground, or you can catch it like this and see what is the top surface, then only two outcomes that we are usually interested in are either head or tail. But we can observe more than just head and tail. Actually, we can ignore this information of head and tail and observe something else. For that, I'll take another object, a thin wooden disc. I take this disc, and this has no marking on any side, so the two sides are same to me. If I toss it just like a coin and let it rest on the ground, I won't be able to tell which side is up because both sides are the same. So what I'll do, I'll put a marker on the edge, and this marker will be used to determine the orientation of the disc when it comes to rest on the ground. When it comes to rest on the ground this way or that way, in such a way that this marker is pointing away from me, then it's the same event. So the observation I'm interested in is that what is the orientation? Is it going to rest this way, this way, this way, this way, or that way? To make these observations formal, I'll put a graph paper on the table or on the ground with clearly marked X and Y axes. On this graph paper, this disc will fall and come to rest. Once the disc has come to rest, I'll observe the orientation of this disc by looking at this line, starting from a point directly opposite this marker and going through this marker. And this line will make an angle of 0 or larger up to 360 degrees with the x-axis. So in this experiment, we are not interested in head or tail of this thin disc, but its orientation as it comes to rest. And this orientation will be an observation in degrees with a value between 0, parallel to the x-axis, or a value slightly less than 360 degrees. Suppose you perform this experiment and actually measure this orientation in degrees. So due to limitations of the measuring instruments, due to finite precision of the measuring instrument, it's quite possible that you will record your observations which are only degrees. So if you record an observation of 45 degrees, then it's possible that the disk was actually making an angle of 44.995 or 45 degrees or 45.02 degrees. So due to limitation and finite precision of your measuring methodology, you observe 45 degrees and 46 degrees and nothing in between. But it's obvious that when this disk comes to rest, it can make any angle with respect to x-axis. So in this case, the observation is orientation, and this orientation lies in the range 0 to 360 degrees, and it's a real valued number. So how many possible values are there? Infinite, uncountably infinite. It can be any real number between 0 and 2 pi radians or 0 and 360 degrees. So these kind of random experiments where the outcome belongs to an uncountably infinite set, an interval on real line, are different from those experiments where the sample space was finite. Only a finite possible outcomes could be realized. In this case, an infinite selection of outcomes is possible. So how do you assign probabilities to such uncountably infinite sample spaces? You again follow the same mathematically precise principle that you form sigma algebras. So sample space is an interval on real line, and sigma algebra consists of subsets of this interval on real line. So what kind of subsets? It will be clear in a while. We only take those subsets which have finite length. Why? The reason is, for finite sample spaces which had only a finite outcomes, if all outcomes were considered equally likely and there were a total of n of them, we could assign a probability of 1 over n to all the outcomes. The situation is not so in the case of those random experiments where the sample space is uncountably infinite. So taking this example of the orientation of the disk, there are uncountably infinitely many possible outcomes, and if you consider all of them to be equally likely, then the probability that you can assign to individual outcome will be 0. So you do not consider individual outcomes in such sample spaces as valid events. So those subsets which only contain one point are not part of the sigma algebra. Sigma algebra in this case, where sample space is an interval on real line, only contains those subsets of that interval which have non-zero length. So only non-zero length subsets are in the sigma algebra. So our events are in the sigma algebra, and our events have non-zero length associated with them. So let's divide this sample space of orientation of a disk into two intervals. One is between 0 and 180 degrees, and the other is from 180 degrees to 360 degrees. So these are two events. So what's the probability of one event occurring versus the other event? If you assume that all outcomes are equally likely, then the disk resting in such a way that pointer is pointing upward is same as the probability of disk resting in such a way that the pointer is pointing downwards, and the two probabilities can be assumed to be half. You can have other subsets of this interval and assign probabilities accordingly. One rule of thumb is that if all outcomes are considered equally likely, then the probabilities assigned to events with non-zero length are proportional to the length of that interval. This can be seen from this slide, which shows that our sample space is set of all omegas belonging to set of real numbers such that omega is greater than 0 and less than 2 pi, where this omega represents the angular orientation of the disk in radians. Let's consider another interesting example. If you have seen footpaths in our country, the central portion where people actually walk is not a continuous one. Usually they place glass strips at regular intervals and fill the rectangular areas between two strips with concrete. I don't know about you, but if I'm walking on such a footpath, I try not to put my foot on the glass strips. It could be a psychological problem, but I feel uncomfortable touching the discontinuity in the footpath. So suppose you have a path like that, which is partitioned with glass strips of a thin width, and these strips are at regular interval, and if you are not looking at your feet while walking, you could be walking randomly and your foot may land anywhere. If you have such a situation, what is the probability that your next step will land on the glass strip? Of course, this is a random experiment. If you are not looking where you are walking, then your foot may land anywhere. It may land in the central region where there is only concrete, or it can land on the glass strip. So what's the probability of your foot randomly placed landing on a glass strip can be found by carefully analyzing this problem and seeing what is the sample space and what part of the sample space will result in your foot landing on the glass strip and what part of the sample space represent your foot landing in the middle part where there is only concrete. To analyze this problem, you have to make a few assumptions. First is that these glass strips are placed at equal intervals. And the other is that your foot always lands perpendicular to the glass strip. So you are not allowed to put your foot in a zigzag fashion. You can solve this problem by assuming numeric values to different quantities. Suppose the glass strips are 75 centimeters apart. So from center of the first glass strip to the center of the next glass strip, the distance is 75 centimeters. And the glass strips themselves are half centimeter thick. And your foot is 30 centimeters long. If you assume these values, you can use them to formulate this problem in a concise numeric way as shown in the next slide. In this slide, only one rectangular region of the footpath is shown and the variable of observation is marked as x and it represents the distance between the front of your foot and the next glass strip, the nearer edge of the next glass strip. If your foot happens to be on top of a glass strip, you will not use that glass strip to find this x. You will always use the glass strip which is not being touched by your foot. So this x can be any number between 0 and 75. This is a real valued quantity and this represents S, the sample space. Our sample space is real valued and it is an interval between 0 and 75 where these numbers represent centimeters and they represent the distance between the front of your foot to the nearer edge of the glass strip in front of your foot. If you look carefully, you will see that your foot will touch a glass strip if this distance lies between 44.5 centimeters and 75 centimeters. So if you assume that your foot will be placed randomly anywhere, and this observed variable x will lie anywhere between 0 and 75 with equal probability, then the interval in which this variable x should lie so that your foot touches is from 44.5 to 75, and length of this comes out to be 30.5, and the probability of your foot touching the glass strip is simply 30.5 divided by 75, the total length of the sample space, and it comes out to be approximately 40.7%. So if you take this simple problem of a continuously varying observation that lies between 0 and 75, then the probability of this interesting event that your foot touches a glass strip is 40.6666% or 40.7% approximate. You can apply these kind of ideas to other problems where the variable of observation lies in a range and can attain any value in that range. Here is another interesting example shown in the next slide. In this slide, a graphical representation of game of bowling is shown. In this game, there is a 60 feet long bowling alley, and at the end of this bowling alley there are 10 pins, and your aim is to throw a big ball at those pins and make those pins fall. Make as many pins fall as possible. And I have searched the web and found out that this big bowling ball is usually with a diameter of 9.6 inches. Even though the pins have variable diameter as the height varies, but for sake of simplicity, you can assume that they are constant diameter cylinders of the maximum diameter, that is 4.5 inches. So if you have placed such constant diameter cylinders at the end of alley and you are throwing a ball at them, then there are many things that can happen. If you are an expert player, then you will hit the center pin, the first pin that is nearest to you, more often and score a lot of points. And if you are an amateur like me, then most of the time your ball will end up in the side gutter. To simplify this problem, let's assume there is an invisible wall that does not permit the ball to go in the gutter, and you throw the ball in a random manner so that ball can go anywhere in that 46 inches wide bowling alley. The ball is not going in the gutter and it is going to cross this area where the pins are standing in a random manner. So what is the probability that if a ball is thrown like that, it is going to hit the head pin? You can see the dimension of the pin, dimension of the ball, and the total dimension of the bowling alley and come up with the answer. I leave it as an exercise. There are other interesting questions that can be put in a probabilistic manner and answered. For example, what is the probability that a randomly thrown ball is going to hit only the rightmost back pin or the leftmost back pin? There are many other problems which can be analyzed by taking sample spaces which are uncountably infinite. And let's look at a couple of them. In the next example, we are going to extend our discussion of partitioned footpath. In this example, we are going to take a room and draw square grid on the floor of the room. And these grid lines are assumed to be very thin, insignificant compared to other quantities in discussion. And these quantities are grid spacing and the diameter of the disk that we are going to throw. So the problem is that we have a room and on the floor we have square grid, parallel lines running this way and parallel lines running this way, and the grid spacing is D. and we have a circular disk with diameter P, and we throw this disk on the floor and see if the disk touches any of the line or not. There is one trivial case that if the diameter of the disk P is larger than the grid spacing, then it's always going to touch some line. So by excluding this trivial case, we are going to assume that the diameter of the disk is smaller than the grid spacing. If that's the case, what is the probability of the disk touching a line? Of course, the answer is going to depend on D, the grid spacing, and P, the diameter of the disk. And this is explained in the next diagram graphically. In this diagram, you see that if the disk is thrown in such a way that the center of the disk is at a distance of P by 2, where P is the diameter of the disk, then the disk is not going to touch any line. So if the center is at least P by 2 away from a crossing point of two horizontal and vertical grid lines, then the whole disk will be inside a square of width D. And if you take all the points of the center of the disk which represent the event that if the center of the disk belongs to these points, then it's not going to touch any of the line, then these points make a square, and the width of that square is definitely D minus P, and the area of that square is D minus P whole square. So if you assume that when you throw a disk, its center is going to lie anywhere on the room, and any point on the floor xy is equally likely with any other point, then the total area of the square is D square, and out of this total area, a smaller square at the center of this square with a width D minus P represent that region which will make sure that the disk does not touch a line. So the probability of a disk thrown on the floor and not touching a line is simply D minus P whole square, the area of the central square, divided by D square. And if you want to find out the probability that the disk does touch one of the line, then that event is complement of this event, and the probability of that event is 1 minus D minus P whole square divided by D square. You can make this problem more challenging by assuming that the floor of the room is marked with 3 sets of lines, one horizontal, one making an angle of 60 degrees with respect to these horizontal lines, and one making 120 degrees. And these lines are drawn in such a way that they form a network of equilateral triangles with all angles equal to 60 degrees. If you have marked your floor using this triangular grid and throw the disk on this floor, what will be the probability of the disk not touching any line? I hope you can see that this will be represented by a smaller triangle inside the big triangle, where if the center of the disk lies, it is not going to touch any of the grid lines. But what will be the value of this area representing the event where the disk does not touch any line? If we have such a triangular grid, then what is the limitation on the diameter of the disk? That is, what is the largest diameter of the circular disk that we can have, and still the disk will not touch some line some of the time. You know, if the disk is large enough, its diameter comparable to the grid spacing, then it's always going to touch some line. I leave this problem as a homework, and I hope you will work hard and find the probability of the disk touching a line as a function of grid spacing and the diameter of the disk. You might have noticed that I have restricted myself to circular disks. What happens if I throw a square-shaped disk on the floor where the floor is marked with a square grid? As it turns out, this problem is much harder than the problem of circular disk, because now not only the central location of the disk, but its orientation is going to decide if it's going to touch a grid line or not. At this moment, we do not have sufficient background in probability theory to solve a problem like that, but we will cover this case in a couple of lectures. You should notice also that in this case where I have thrown a disk on the floor, my observation is a vector valued observation. It is x and y, where x is the displacement of the center of the circular disk from a vertical grid line, and y is the displacement of the center of the disk from the horizontal line. So in this experiment, I make two observations, and they are x and y, because the plane is being used to make the observations. It's possible to make observations on higher dimensional space, 3-dimensional or even 4-dimensional space. But the key idea is that in these problems, the sample space consists of intervals on real line, region on plane, or some region in space. Let's look at another example where real valued, continuously varying observations are made. Suppose we are talking about a city, a modern city, which has underground trains which residents use to go from one place to another. Furthermore, there are two major lines. One runs north-south and other runs east-west. And there is one station in the downtown or financial center of the city where these two lines cross each other. And that downtown station is considered a junction, which can be used to change train. If you are traveling on north-south train, you can get off that train and take an east-west train. Now, as the trains run every 10 or 15 minutes, they come at a random time. By random time, I mean when you enter a station, you don't know if the train has just left or is it going to arrive in next few seconds. For you, when you enter, the time starts, the time for you to wait for the train. And this can be anywhere between 0 and say 10 minutes. So this observation of entering the railway station, the underground railway station, and noting the time that you have to wait before you get your desired train is a random experiment. It's a random observation, and it lies continuously between 0. 0 is the case when you enter the train and the train is standing there waiting for you. And the maximum value is the time it takes for the next train to come. You can analyze this problem using continuously valued observations of waiting time, and you can do more, particularly for that station, the downtown station. There you can observe the waiting time for both trains. Then your observation is a vector, two-dimensional vector, where first entry could be the waiting time for east-west train, and the second entry could be the waiting time for north-south train. So you can formulate this problem and answer many interesting questions. For example, one question is that if a person enters the railway station at a random time, what is the probability that he will see the east-west train standing there waiting for him? To answer that question, you have to know a few things numerically. One is that what is the time between two trains? Assume that when a train comes on the east-west line, when the train comes, it stays there for 3 minutes and then it departs. And after a train departs, the next train comes after 10 minutes. So the maximum waiting time is 10 minutes and minimum is 0, as we have already discussed. So when a person enters the train station at a random time, what is the probability that he will see the train there and he will not have to wait at all? If you look at the sample space of this random experiment, you will see that the train departure time can have a value of 0 to 13 minutes because the train comes 10 minutes after the departure of the previous train and then stays there for 3 minutes. And the event that the person enters at a random time and sees the train standing there is represented by the 3 minutes of those moments when the train is standing there. So out of a total of 13 minutes, the train spends 3 minutes standing at the station. So if the person is equally likely to enter any time between these 13 minutes, the probability of him not waiting at all and getting the train as soon as he enters the station is 3 divided by 13. Similarly, if you assume that the north-south train runs in such a manner that when it comes, it stops for 2 minutes and then departs. And the next train comes 10 minutes after the previous train has departed. So the north-south train runs at a frequency of 12 minutes. Out of these 12 minutes, 2 minutes are spent waiting at the station. So in this case, for a person who wants to go on the north-south line, the probability of not having to wait is 2/12. But on that downtown station, many more very interesting experiments can be performed. There are many interesting events, joint events that can be looked into and assigned probabilities. For example, suppose a person is coming from south on the north-south line and he plans to get off that train and take a train which is going towards east. Then what is the probability that he will have to wait 2 minutes or less on that central station before he gets the next train? It's possible that he has to wait more than 2 minutes, but the probability of having to wait less than 2 minutes is of our interest. To solve this problem, we have to have a two-dimensional sample space where x-axis will represent the time associated with east-west line and the y-axis will represent the times associated with north-south line. I have this two-dimensional sample space in the next slide. If you look at this slide, you will see that this two-dimensional sample space is represented by a rectangular region, and this rectangular region spans x extent of 0 to 13, where first 10 minutes are shown as white and next 3 minutes are shown as gray area. Similarly, the vertical extent of this rectangle is 12, where first 10 units are shown as white and next 2 units are shown as gray area. These gray areas represent the time when the train is standing at the station. So north-south train stands at the central station for 2 minutes and the east-west train stops at the central station for 3 minutes. Now that we have this two-dimensional sample space where x-axis represents the waiting time for the east-west train and the y-axis represents the waiting time of north-south train, we can make interesting events, joint events, depending upon both trains and assign probabilities to them. The first event that we are going to consider, as shown in the next slide, is that the north-south trains comes after the east-west. Even though the trains continue to run after 13 minutes or 12 minutes for east-west and north-south lines respectively, but we are interested in such an event that the north-south trains arrives after the east-west and slightly later, not much later. Because if north-south train arrives much later, then the east-west train, the next east-west train will arrive soon after, and we are not interested in that event. As shown in this slide, this interesting event is represented by the triangular region, the upper triangular region of the sample space. This triangular region is represented by all those points x, y, where y is slightly larger than x. You can assume this case to be a case where a person enters the station, the central station, at a random time, but has no intention to board any of the train. He is just making observations about different trains coming and going. So he enters at a random time, and then he sees the east-west train coming first and north-south train coming slightly later. And this event is represented by the upper triangular region. Here is an interesting but challenging question. What is the probability of two trains reaching the station simultaneously? That is, what is the probability of those points x, y, where x is equal to y? Even though in real life we might perceive that two trains have reached the station simultaneously, but in probability theory we cannot assign probabilities to these events, because these events consist of collection of points in such a way that the collection does not have an area. Just like for one-dimensional infinite sample spaces, you cannot assign probabilities to isolated points. You can only assign probabilities to regions with non-zero length. For joint two-dimensional probabilistic sample spaces, you cannot assign probabilities to points or lines. You can only assign probabilities to events represented by regions of sample space with non-zero area. So this event of two trains arriving simultaneously is represented by the thin diagonal line, the line where x is equal to y, and this event cannot be assigned a probability. But this event can. That is, what is the probability that when the north-south train comes, it sees the east-west train standing, and when the north-south train departs after 2 minutes, it still sees the east-west train standing there. This can happen because the north-south train only stops for 2 minutes and east-west train stops for 3 minutes. So when this train comes, suppose a few seconds after the east-west train, it will spend its 2 minutes and departs, and then as it is departing, it will still see the east train standing. As it turns out, if all these events are equally likely with reference to the starting time of the person entering a station, then all these probabilities are proportional to areas. So the previously discussed event where we assumed that the north-south train arrives slightly later than the east-west train has a probability which is the ratio of the area of the upper triangular region divided by the whole area of the sample space. This problem has been worked out in your class handouts. You should have a look at those, and there are some homework problems or extensions of the discussed problems, more challenging extension that you should work out to have a better understanding of uncountably infinite extent sample spaces. Our next example also involves uncountably infinite type of sample space, and it also involves throwing things on the ground. It's a famous problem, and it's called problem of Buffon needle. It's called so because it was first proposed by a naturalist, Georges Buffon. In this problem, we take a floor and mark it with horizontal lines with a certain grid spacing or line spacing. Let's call this D. And then, instead of taking a circular disc, we take a small needle and we throw the needle on the floor with horizontal lines, and then try to determine through a mathematical model what will be the probability of the thrown needle touching one of the lines. You can have a variation of this problem where you can mark the floor in a square grid and then throw a needle. In that case, there is one trivial case that for a square grid, if the length of the needle is larger than the diagonal of the square, it is always going to touch some line. But for that case where there are only horizontal lines, a big needle can land in such a way that it does not touch any line. So that case is more interesting. So you take a floor, draw lines on that, and then throw a small needle and find out probability of that needle touching a line. As it turns out that we cannot solve this problem with the usage of the tools that we have discussed so far. So far we have discussed things to be equally likely in the continuous intervals. If we apply that rule here and assume that it is equally likely for the center of the needle to be anywhere between two neighboring lines, and it is equally likely for the orientation of the needle to be of any value between 0 and 360 degrees, then the expression for the needle touching a nearby line is quite involved, because if the needle is in the center of two lines, then the probability of it touching depends on the orientation in a different way compared to the probability of it touching when the center of the needle is very close to the line. Furthermore, there are two distinct cases where the length of the needle is less than the grid spacing, the spacing between horizontal lines. In that case, when the needle is lying vertically, it is possible that it is not touching a line. But if the needle is longer, then it is lying vertically, then it is definitely touching one of the line. The only way it can not touch a line is if it is lying at an angle. So all these things make this a difficult problem to analyze, and to analyze it properly, we need concepts of random variable, particularly continuous valued random variables, and the concept of density function. Once we have covered these ideas of random variables and density functions, we will be able to analyze the problem of Buffon's needle. Not only that, I hope we'll be able to analyze that problem I discussed in today's lecture, where in a square grid we throw a square shaped disk, and that problem also needs the ideas of random variables and density functions. These ideas will be discussed in the coming lectures. In today's lecture, we covered many things. We concluded our discussion of Bayes' rule and applied it to a simple but interesting problem. Then we started the discussion of continuous valued observations and uncountably infinite sample spaces. We discussed one-dimensional as well as two-dimensional continuous valued observations and continuous valued sample spaces. And then we defined events in those continuous valued sample spaces, and simple assumptions were used to assign probabilities to those events. And the simple assumptions were that the outcome was equally likely to have occurred in the range of the sample space. And if you want to go beyond that, you want to consider cases where things are not equally likely, you need other ideas that will be discussed in coming lectures, and then we'll be able to discuss, analyze, and assign probabilities to more challenging, continuous valued problems. Till then, I wish you best. Thank you. Khuda Hafiz.